The paper discusses the significance of personalized item ranking in recommender systems, focusing on the approach of pairwise ranking through constructing positive item, negative item, triplets. It highlights that treating all triplets equally may not achieve the best effects, as different triplets contribute differently to the model training performance. The authors propose the Triplet Shapley method, which uses Shapley values to measure the importance of each triplet in an interpretable manner. This method transforms the original Shapley value calculation to a Monte Carlo approximation, with a guarantee for the approximation's unbiasedness. To stabilize the Monte Carlo approximation, a control covariates-based method is adopted. The authors also utilize the Triplet Shapley value to guide the resampling of important triplets for model learning. They conduct extensive experiments on 6 public datasets involving classical matrix factorization and graph neural network-based recommendation models, showing that their model consistently outperforms state-of-the-art methods. The paper emphasizes the need for more interpretable and equitable triplet importance, proposing a gradient descent-based Monte Carlo approximation method to compute the Triplet Shapley. It also presents an importance-aware resampling method to collect more high-importance triplets into the original triplet set, contributing to the model training. Interpretable Triplet Importance for Personalized Ranking, ITIPR, is a novel method that utilizes Shapley values to assign importance scores to each user-item interaction triplet in a recommendation model. This approach aims to enhance the model's performance by focusing on the most informative interactions during training. The authors propose a control variates-based estimator to approximate the Shapley values efficiently, utilizing a modified gradient descent algorithm to obtain an accurate value for a known control variate. This method facilitates the selection of an optimal constant to minimize the variance of the estimator. The paper also introduces an importance-aware triplet resampling strategy, which uses a neural network model to predict the Shapley values for potential triplets not initially sampled into the training set. This strategy guides the resampling process to ensure that high-importance triplets are adequately represented in the training data. The overall learning procedure of the proposed method is summarized in an algorithm, which involves triplet importance approximation, importance-aware triplet resampling, and triplet importance-weighted pairwise learning. Experimental evaluations on several public datasets demonstrate the effectiveness, applicability, interpretability, and time efficiency of the proposed method. The results show that the method can achieve better recommendation performance than various baselines, provide a reasonable explanation for the importance scores assigned to each triplet, and effectively reduce the training time cost. A comparative study with baseline models such as MF, NOI-MF, NGCF, and Light GCN on 6 public datasets reveals that ITIPR consistently outperforms these baselines across different metrics such as recall at 2.0 and NDCG at 2.0. An ablation study further highlights the crucial contributions of 2 key components in ITIPR: Triplet Shapley-weighted pairwise learning and Triplet Shapley-aware resampling. A case study illustrates how ITIPR can provide insights into user preferences and item importance, effectively identifying the most influential items in a user's interaction history. Overall, this research contributes to the development of more accurate and interpretable recommendation models by leveraging the concept of Shapley values and importance-aware resampling strategies. In personalized ranking models, the concept of Triplet Shapley values is introduced to measure the importance of triplets, providing a nuanced understanding of each item's contribution to the model's performance. A Monte Carlo method with control variates is proposed to reduce the variance in estimating the Shapley values, accompanied by an importance-aware resampling strategy to enhance model training. Experiments on 6 datasets demonstrate the effectiveness and efficiency of the approach, with Triplet Shapley values exhibiting reasonable and intuitive scores. A stability analysis shows that the estimation variance can be greatly reduced using the control variates-based stabilizing strategy. The time complexity of various methods is discussed, highlighting the competitiveness of the proposed approach with previous state-of-the-art techniques. The paper outlines a novel framework for interpretable personalized ranking, focusing on triplet importance for user-item interactions based on Shapley values. Notations and definitions are introduced for the triplet construction space, sampled triplet set, and triplet importance weights. Two categories of base recommendation models are discussed: matrix factorization-based models and graph neural network-based models, including popular instances such as MF, NOI-MF, NGCF, and LIGHT-GCN. The methodology involves computing the Shapley value for each triplet in the interaction data, with proofs provided for three theorems related to the unbiasedness and consistency of the proposed method. The time complexity of the method is analyzed, demonstrating acceptable time efficiency for large-scale recommendation systems. Overall, the paper presents a novel and interpretable approach to personalized ranking, providing insights into the importance of each user-item interaction and improving the transparency and accountability of recommendation systems. This paper introduces a novel method for personalized ranking in recommendation systems, focusing on interpretable triplet importance. The proposed approach utilizes the Shapley value to assign importance scores to triplets, which are then used to rank items for users. The method is evaluated on 6 public datasets, including Amazon Books, Amazon CDs, Yelp, Gowalla, ML20M, and ML Latest, with data statistics provided in Table 5. The algorithm's complexity is significantly reduced through the use of Monte Carlo approximation and truncation operations, bringing it down to O(V) squared, in practical terms. Furthermore, the Monte Carlo process can be parallelized up to the number of interactions, further reducing actual time consumption. To optimize the method, the authors suggest dividing items into coarse groups based on their property similarity, reducing time consumption while maintaining accuracy. The supplementary section provides full descriptions for the datasets used in the experiments, detailing the preprocessing steps and filtering thresholds applied to each dataset. The Shapley value, a concept from cooperative game theory, is used to fairly distribute the total importance among triplets, providing an interpretable measure of each triplet's contribution to the ranking process. By approximating the Shapley value using Monte Carlo methods, the algorithm can efficiently handle large datasets. The truncation operation reduces the number of interactions considered, further improving computational efficiency.